So first of all, I'm going to be discussing and talking about Snell's law. So first, I want to discuss upon a point. So when light travels from one medium to another, it generally bends or refracts. So the law of refraction, or Snell's law, is it gives us a way to determine the amount of bend that a wave sees when it travels into a different medium. So yeah, in this sense, a wave is traveling from one medium into a different medium, and this involves an incident wave and a refracted wave. So, incident ray and a refracted wave. Okay, and this relationship that we can find from the incident angle and the refracted angle of the wave of the rays can be determined and they can be quantified through Snell's law up here. So, I want to talk about this first case in which we have an incident wave and a refracted wave here. And this is when it's passing from a less dense medium, such as air, into a denser medium, such as water. So when this happens, the wave is going to travel to the boundary, and once it hits the boundary, it's going to bend, and the angle of refraction is actually here, and it's going to get smaller because now it's going from a less dense to more dense, and the wave is going to slow down and it's going to get closer to the normal. And this line, dotted line right here that I'm pointing at, is going to be the normal line. So these calculations will go after, but we can first talk about a different scenario in which we have this scenario. And this is what I'll be discussing: the total internal reflection and the critical angle. So first, when an incident wave here strikes a boundary in which it goes from a more dense medium to a less dense medium, the wave is also going to refract, but instead of going closer to the normal, it's going to go further away from the normal, as shown here, where this is going to be our incident angle, and this is going to be our, don't ignore this is incorrect, but this is going to be our refracted angle right here. So first I want to, before I talk about critical angle, I want to also say that when an angle hits and strikes here, part of the light is always going to reflect no matter what, so which is shown in the dotted line right here. So then I want to talk about the critical angle, and the critical angle is actually an angle at which once you increase this angle right here, there's going to be a point where your refracted angle is actually 90 degrees, or we can say that it's parallel to the actual boundary, which is shown right here. A different scenario, yeah, this is our critical angle. The critical angle is the angle at which it creates a refracted angle that is parallel to the actual boundary. Now, once we go, now increase the angle greater than the critical angle, the incident wave is actually going to reflect from the boundary and go back upwards and stay in the more dense area. And this angle of incidence is actually going to be reflected on here, and these are going to be the same two angles. So the total internal, this is actually total internal reflection, and this is when all the light will be reflected back and remain in the denser medium because it's actually greater than the critical angle. And we can also prove this, and we can also say that the refraction index, which we have part of our equation over here, this is also Snell's law, but our refraction index of the dense material can be set as 1 over sine of the critical angle. This can be proven by, because through Snell's law, we said that the refraction index of our first medium over our second medium, okay, and that's going to be equal to the sine of this angle, the incident wave, or incident angle, or the incident or the refracted angle. We can say that it's going to be a refracted angle over the incident angle. And since it's going to air, we all know that the refraction index of air is 1. So here now we can say that the dense material, which will be N2, can cancel out because the 1's going to cancel out. And since sine 90 degrees is equal to 1, we can say that the refraction index of the dense material is going to be 1 over sine critical angle. Yeah, I want to explain that real quick as well. This was the incident angle, and this was the refracted angle. And this is actually, yeah, like stated before, this is stated to Snell's law, and the relationship is shown here. Now I'll show a quick calculation based upon this data. Based upon this data, we can say that since, for example, we have a case where a wave is traveling through a medium of water and then passes a boundary into a different medium where it passes through air now. We know that the refraction index, and the refraction index is actually the sign over that, and we can find the refraction index. So we know our refraction index of water is 1.33, and the refraction index of air is just 1. So through Snell's law, we can say that the refraction index of 1.33, which is the one of water, over the refraction index of air equals that, can be said over sine theta r, which say this is unknown, cancel this out, and we know this. That would be 30 degrees because we know this. From there, we can carry out a calculation with cross multiplication that 1.33 sine 30 degrees equals our sine r, which is our angle of refraction. And then from there, we can calculate the inverse sine, and then we can find the angle of refraction through these calculations. I hope that was clear and I hope that was well explained. Thank you so much for listening. And wait, I want to show one more thing here. This is the showing how the incident, the critical angle. So the greater you increase this, it's gonna hit a degree of 90, and this would be like our critical angle. And once you increase this, it will go further. So thank you for listening, and yeah.